Hello students, welcome to this lecture on adaptive filters. Recall that the LMS algorithm updates the filter weights according to this relation. H of n plus 1 is equal to Hn plus mu times En into Yn. Yn is the data vector, En is the error, and Hn is the filter coefficient at instant n. Under the independence assumption, the LMS algorithm is convergent in the mean if the step size parameter mu satisfies this condition. We know that mu should be less than 2 by lambda max. And E of Hn converges to the corresponding winner filter weights. As n tends to infinity, E of Hn converges to the corresponding winner filter weights. Under the independence assumption, the MAC epsilon n converges if and only if, again first condition is like this, mu is less than 2 by lambda max, and the second condition summation mu lambda I divided by 2 minus mu lambda I going from 1 to m should be less than 1. We also noted that the convergence of the LMS algorithm is slow when the eigenvalue spread of the autocorrelation matrix is large, and there is a misadjustment factor, that is the ratio of the excess mean square error divided by the minimum mean square error corresponding to winner filter, and that is approximately equal to half of mu times trace of Ry. Therefore, this misadjustment factor will be large if mu is large, therefore, mu should be small. This lecture will cover the variants of LMS algorithm addressing the above issues, convergence issue. We also see two simplifications of the LMS algorithm for faster implementation. First, we will start with the Leaky LMS, NLMS algorithm. We saw that the LMS iteration is convergent in the mean if the step size parameter mu satisfy the convergence condition in terms of the eigenvalues of Ry matrix. So, the convergence is determined by the eigenvalues of Ry matrix. If some eigenvalues are small, the convergence will be slow. Thus, if any one of the eigenvalues is small, then the rate of convergence will be affected. Therefore, to improve the convergence rate, the small eigenvalues may be enhanced. One method to improve the convergence is the Leaky LMS, NLMS algorithm. It uses a leakage factor to control the values of the filter coefficients in LMS updation. This is the LMS updation. H of n plus 1 is equal to Hn plus mu En into Yn vector. Let us examine the cost function for NLMS algorithm. The cost function of the Leaky LMS algorithm includes a regularization term. Thus, the minimization problem can be expressed as minimize square n plus alpha times norm of Hn square with respect to Hn, where norm of Hn square is equal to H transpose n times Hn. This is the Euclidean norm. Alpha is a positive quantity, and En is dn minus, that is the desired signal, minus Hn into Yn. This is the filtered output. So, here square n is the cost function corresponding to the LMS algorithm, and this term alpha times norm of Hn square is the regularization term. The term alpha times norm of Hn square ensures that Hn decreases faster, because if it tries to increase because of this positive value, the cost function will increase. So, our aim is to minimize the cost function. Alpha is taken between 0 and 1, and the method of gradient descent is applied to minimize the above cost function, just like in the case of LMS algorithm. The corresponding update equation is given by Hn plus 1 is equal to 1 minus mu alpha times Hn plus mu alpha into En plus En into Yn vector. So, the leakage term is introduced here now, where mu alpha is chosen to be less than 1 because of this factor is to be positive. So, mu alpha must be less than 1. Using the independence assumption, we can show that limit E of Hn as n tends to infinity is equal to Ry plus alpha I whole inverse into small r dy. This is the cross correlation between d and y. Note that this is different from the corresponding Wiener filter solution. We see that the matrix alpha I is added to the correlation matrix of LMS iteration. LMS iteration correlation matrix is Ry. In Leaky LMS, this matrix is added, alpha times I matrix is added. We also note that alpha I is the autocorrelation matrix of a white noise with variance alpha. So, if we have a white noise with variance alpha, then its autocorrelation matrix will be alpha, then rest of the elements in the first row will be 0 like that. Similarly, second row this will be 0, then alpha 0 like that, and finally, the last row will be 0, 0, 0, and that last element will be alpha. So, that way this will be the autocorrelation matrix of the white noise, which is same as alpha times I. Therefore, the regularization process, a white noise component is added to Yn. To the data, a white noise component is added, that way it is pre-whitening of data. Now, let us examine the convergence condition for the Leaky LMS algorithm. If lambda I is an eigenvalue of Ry, then the corresponding eigenvalue of Ry plus alpha I will be lambda I plus alpha. So, each eigenvalue will be increased by alpha. Therefore, for convergence, the constraint on mu is mu should lies between 0 and 2 by lambda max plus alpha. Next algorithm, we will consider the normalized LMS, NLMS algorithm. Consider the LMS update equation given by h of n plus 1 is equal to Hn plus mu times E of n into Yn vector. For convergence, this mu should be less than 2 by lambda max, and the conservative bound for convergence is given by mu less than 2 by trace of Ry, and that is equal to 2 by m times, m is the number of filter coefficients, m times Ry 0, and Ry 0 we can write it as expected value of E of y square n. Therefore, for convergence, mu should be less than 2 by m times E of y square n. Note that Ry is not generally known, Thus, lambda max or RY of 0 is to be estimated from the data. This expression E of y square n is to be estimated from data. We can avoid this problem by using the estimate 1 by m times summation y square n and going from 0 to m in place of E of y square n, and estimating the bound as 0 is less than mu less than 2 by this expression, because m and 1 by m will get cancelled. Therefore, 0 is less than mu less than 2 by summation y square n minus I going from 0 to m minus 1, and that is equal to 2 by norm of y n square. Now, because mu is less than 2 by norm of y n square, so we can take mu is equal to beta times 1 by norm of y n square, where beta is a number between 0 and 2. We can take any value of beta between 0 to 2, but it is chosen to control the misadjustment factors. Smaller value of beta will give less misadjustment factor. The convergence of the NLMS algorithm is faster irrespective of the choice of beta in the above range. If we choose beta in this range, the convergence of the NLMS algorithm will be faster than the corresponding speed of the LMS algorithm. Thus, the LMS updating becomes h of n plus 1 is equal to h n plus beta times 1 by norm of y n square times E n into y n. Note that multiplication by 1 by norm of y n square changes the step size according to the variance of the signal magnitude, but it does not change the direction of the gradient given by y n, because y n will specify the direction of the gradient. This y n is a vector and E n is a scalar. Therefore, y n specifies the direction of gradient, and multiplying by this factor will not change the direction of the gradient. If y n is close to 0, then the denominator term, that is norm of y n square here, becomes very small, and in that case this expression h n plus beta times 1 by norm of y n square into E n into y n may diverge, because this term may blow up. A parameter gamma is included in the denominator to avoid large step size when norm of y n square becomes close to 0. So, therefore, ultimately h of n plus 1 will be equal to h n plus beta times 1 by gamma plus norm of y n square into E n into y n vector. So, this is the NLMS update rule. We can briefly state the NLMS algorithm. So, here given the input signal y n, desired signal d n, filter length m, beta less than 2 and a small constant gamma. Initialization h I 0 is equal to 0 for I is equal to 0 to m minus 1. All filter coefficients are initialized to 0. For n greater than 0, filter output will be d hat n is equal to h transpose n times y n. This is the filter output. Estimation error E n is equal to d n minus d hat n, and filter coefficient is updated according to this relationship. NLMS update rule, h of n plus 1 is equal to h n plus beta times 1 by gamma plus norm of yn square into En into Yn vector. We will consider one example of system identification with the LMS and the NLMS algorithms. System identification problem we introduced in the first class of adaptive filters. The problem is like this: you are given a 5-length FIR system with unknown parameters, identify them using adaptive filters. So, here it is a 5-length FIR system. We know that there are 5 coefficients in the FIR system model. We have to identify those 5 parameters using a 5-length FIR adaptive filter. So, here Yn is the input to both the system and the adaptive filter, and usually Yn should be a white noise. And the desired signal Dn is the output of this unknown system, and the adaptive filter will estimate this desired signal, and this error signal is fed back to the LMS or NLMS update algorithm. So, that way the 5-length adaptive filter is updated using the LMS and NLMS algorithm. We show the simulation result. So, this is the original system, 5-length FIR system. These are the filter coefficients. One coefficient is 0, here 0. This is the another coefficient, third coefficient is like this, fourth coefficient is like this, and fifth coefficient is like this. And after identification by LMS algorithm with mu is equal to 0.5 and data length is 200, we get this result. We see that this coefficient originally it was 0.44 like that, here it is much near 0.3. So, it is not exactly estimating. Similarly, this coefficient also it is not exactly estimating. If we identify the FIR system using the NLMS algorithm, we get the estimated results like this. Now, this value and this value, similarly this value and this value are almost matching. There is a small difference, but because it is 200 data only, with that itself it is matching very well. Thus, we see that the NLMS algorithm converges faster than the LMS algorithm. Let us quickly discuss the merits of the NLMS algorithm. Under the independence assumption, it can be shown that the NLMS algorithm converges in the mean square sense, provided beta lies between 0 and 2. The NLMS algorithm has more computational complexity compared to the LMS algorithm because of the computation of norm at every instant. Note that norm of Yn square is equal to summation y square n minus I going from 0 to m minus 1. This summation we can rewrite as summation I going from 0 to m minus 1 y square n minus 1 minus I. We are considering the earlier instances starting from n minus 1. Then we have to add y square n, because here n minus 1 I going from 0. So, first term will be y square n minus 1. So, y square n we have to include. Similarly, that last term here will be y square n minus m minus 1, and therefore, this term should be subtracted. Therefore, this norm of Yn square can be written as norm of Yn minus 1 vector square plus y square n minus y square n minus m minus 1. So, that way norm of Yn square can be estimated recursively. Only this part we have to calculate this part and then add to earlier estimate of norm square. If yn is close to 0, the denominator term norm of yn square in NLMS equation becomes very small, and this term hn plus 1 is equal to hn plus beta times 1 by norm of yn square into en into yn vector may diverge. To overcome this drawback, a small positive number epsilon is added in the denominator term of the NLMS update equation. Thus, h of n plus 1 is equal to hn plus beta times 1 by epsilon plus norm of yn square into en into yn vector. This is the modified NLMS update rule. Now we will discuss some LMS based algorithms which reduce complexity. In many applications like high speed digital communication, faster adaptation is needed. For such applications, computational efficiency is very important. For this purpose, modifications are suggested to the LMS algorithm. A number of modifications are available. Some of these include block LMS algorithm, signed error LMS algorithm, signed data LMS algorithm, sign LMS algorithm, etc. We will briefly outline the block LMS algorithm and the signed error LMS algorithm. First, we will see the block LMS algorithm. In block LMS algorithm, the input signal is divided into blocks of length L each. So, processing will be done in a block of L inputs. The filtering output for the kth block is given by this Dept kl plus I is equal to H transpose k into y kl plus I. This is the vector, data vector, I going from 0, 1 up to L minus 1. So, that way we will be considering, suppose this is fixed now, but for different data in this block, that is kl plus 0, kl plus 1, etc., those data vector we will be considering and filtering. Now, this is the filtering operation. Since Sk is fixed now, because in one block only one filter coefficient vector will be used, therefore, the filtering operation is efficiently performed by using FFT. So, you can use FFT to perform this. The error is estimated as E of kl plus I, that is equal to dkl plus I minus d hat kl plus I going from 0, 1 up to L minus 1. This is the filtering error. Now, the filter weights are updated blockwise according to this updating rule. H of k plus 1 vector, that is equal to Hk vector plus mu times 1 by L into summation E of kl plus I into y kl plus I vector, I going from 0 to L minus 1. This is done for each data point in the block. So, that way here we see that the error into that data vector, these are summed up and then divided by L to get the estimate for the error into data vector. So, this is the block LMS updating rule. Block LMS algorithm has the same convergence characteristics as the LMS algorithm with a larger excess mean square error. It can be shown that its excess mean square error is larger. Next algorithm is sign error LMS algorithm. Consider the LMS update rule. H of n plus 1 is equal to Hn plus mu into En into Yn vector. So, this is the LMS update rule. H of n plus 1 is equal to Hn plus mu into En into Yn. Note that the estimated gradient direction is given by Yn. This is the vector. This vector gives the estimated gradient direction. And multiplication by En does not change this direction except when En changes sign. So, if En is negative, this direction will become negative. So, that way only that role is performed by En. Therefore, for faster updating, H of n plus 1 is equal to Hn plus mu into sin of En into Yn. So, where sin of En is equal to 1 if En error is greater than 0 is equal to 0 if En is equal to 0 and minus 1 if En is less than 0. This sign error algorithm can be derived using mod of En in place of the LMS cost function square n. If we use mod of En in place of square n, then by applying the steepest descent, we can derive this updating rule. So, that way it necessarily follows from this cost function, mod of En cost function, absolute error cost function. The signed LMS algorithm is equivalent to the LMS algorithm with 2-bit quantization. So, we have 3 values of error, that is 1, 0 and minus 1. So, that way it is 2-bit quantization. Therefore, the convergence is poorer in the case of this algorithm, because instead of using the entire error, we are using it in 3 values only. Let us summarize the lecture. The cost function of the Leaky LMS NLMS algorithm includes a regularization term resulting in the problem, that is minimize square n plus alpha times norm of Hn square, where alpha is a constant. The term alpha times norm of Hn square ensures that Hn converges faster. So, this is the regularizing term. It ensures that there is no mass deviation between 2 iterations. The LLMS update equation is given by H of n plus 1 equal to 1 minus mu alpha times Hn plus mu into alpha into En into Yn. So, this is the update equation for LLMS algorithm. The normalized LMS NLMS algorithm uses a variable step size given by this relationship. Mu is equal to beta into 1 by norm of Yn square, where beta lies between 0 and 2. To ensure convergence, when norm of Yn square is small, because if Yn become very small, then this quantity will become small and this will diverge. Therefore, to ensure convergence when norm of Yn square is small, NLMS updating is modified as H of n plus 1 equal to Hn plus beta times 1 by epsilon plus norm of Yn square into En into Yn. So, this epsilon is a small positive constant which ensures that there is no divergence. For some applications, computational efficiency is very important. For this purpose, modifications are suggested to LMS algorithm. Two such modifications are block LMS algorithm and signed error LMS algorithm are efficient for hardware implementation. We knew that block LMS that filter coefficients are updated after a block of data. In sign error LMS algorithm, instead of En, sign of En is used in the LMS updating equation. So, we have discussed about LMS algorithm. Next, we will discuss another approach to adaptive filtering, that is recursive least square algorithm. Thank you.